Hello, everyone. Thank you all for joining us today. I'm really excited about today's presentation because if you're interested in the use of AI, I think we've got some really exciting stuff to share with you. It's one of the things that, in my experience, AI is really good at is debugging issues, and we're going to talk a little bit about how you can do that with a tool called LogicStar, as well as LocalStack, obviously. So let me get started here. So today we're talking about building autonomous software systems with AI agents and telemetry. We'll get to, that sounds like a lot of big words, so we'll get to explaining that in just a moment. So this is our agenda. You're in the intro and welcome right now. Thank you all for being here. We're really excited that you joined us. There is a comment section. Go ahead and feel free to join the comments. We like to have a lively discussion while we're hosting this. It always makes it a lot more fun for everybody. So we've got two sessions coming up for you. First, we've got autonomous bug fixing through AI agents that detect, reproduce, and repair by Boris Paskalev. I hope I pronounced that right, the last name. But so Boris is going to be talking a little bit about LogicStar, which is a tool that does these issues. He's the founder of the company. And then we got Lazar Kanelov. I hope I'm pronouncing these right. Apologies if I'm not. He's going to be talking about creating self-healing software systems via effective usage of telemetry data and AI agents. So this is going to be a little bit more of like the implementation of LogicStar into a system like LocalStack. So you're going to see how we actually used it internally. I think it's going to be a lot of fun. So, and then, we'll finish up with some Q&A on both of those sessions. So feel free to put your questions in the chat throughout. We will try to answer them as we go along, but if you don't get answered during the presentation, we will definitely answer them at the end. We'll make sure your questions get addressed. So feel free to just kind of chat. So I am not Kaya Imani. As you might have noticed, this is not me. We had some technical difficulties this morning, which is why we started just slightly late here. That caused me to step in as the host, unfortunately for you, because I don't quite have the charisma of Kaya, but you're stuck with me due to technical issues. But I'm going to go ahead and introduce our speakers here. So we've got Boris and Lazar. Welcome, guys. Boris, why don't you go ahead and introduce yourself?
Hey, thank you very much, Brian and Kaya. I'm sure she's still listening. Boris Paskalev here. I'm one of the co-founders of LogicStar. We're a Swiss-based startup. And again, as Brian highlighted, we're focusing on the future of AI platform that fully autonomously finds, identifies, reproduces fixes, and validates that the fixes are correct for the software development and commercial applications.
Awesome. And Lazar, why don't you introduce yourself?
Hello, and thanks for having me. It's a pleasure to be here. My name is Lazar, and I'm a EM on the core engineering team here at LocalStack. And before joining LocalStack, I worked as a senior engineering leader in several other companies, industries, across different business domains, as well as an architect and advisor before jumping into the management track. So very excited to be here.
Awesome. Well, we're glad to have you both here. Okay, so we are going to go ahead and get started with the presentation. So I'm going to say goodbye to Lazar for right now, and we'll have Boris tell us about autonomous bug fixing through AI agents. So I will go ahead and put your presentation on the screen. Here we go. There we go. All right.
Thank you, Brian. Thank you. Appreciate it. And again, as I said, it's been a pleasure for me to work with the LocalStack team and Lazar as well. So that's why we are kind of co-presenting here, which is great. We're going to speak about autonomous software systems and specifically AI agents, and then Lazar is going to go deeper in the telemetry part. Ultimately, I just want to get the analogy here, like everybody know what SREs are, like software reliability engineers. We are in a way creating the autonomous application reliability engineers. The idea is to proactively try and fix a lot of the problems that are out there, identify them, and prevent issues from actually impacting customers and production. Just some background what we are. Again, I'm not alone here. I'm presenting what we're going to cover today, right? Again, the goal is to improve product quality and increase the engineering velocity in teams. While we're doing that, we're seeing with the AI coding tools, they actually boost developer velocity and speed, but the application quality and maintainability drop, right? And this is where this demand for application reliability engineer comes along. It's not a common term, but it's pretty obvious what it means. And I'm going to show some actual data. Why we're seeing that? That's purely based on data that we're seeing out there. And then how we're doing that, again, this is where the focus of LogicStar is. It's, again, trying to automatically fix qualified issues that LogicStar can deal with autonomously. And when I say autonomously, I do mean 90%. And we'll deep dive into that there. Jumping in, again, behind me, it's not only me. We have kind of a great team, about 13 people right now, a number of additional researchers that are not full-time as well. Again, pioneers of the AI for code back in the days around 2016. We built a deep code and we reached 3 million contributing developers in the open source community, which was great. People using it. Then that actually got merged into Sneak Code, and now that's running more than 100 million ARR in sales, specifically focusing on security. Behind the teams, we've had 2 unicorn products so far, 4 successful exits, hundreds of years of commercial experience. Highlight some of the bigger ones like Google, IBM, Motorola. But also today, we're actually the global leader in lots of the benchmarks in the software, in AI for code and agents for code. The SWE benchmark, we're state of the art there. The SWT, this is a benchmark for the ability to test specific parts of the code and fixes. And finally, the one that we've actually developed ourselves is the SWA, which stands for applications rather than just libraries that are being tested in the SWE. But if we have time, I'll go a bit deeper into those. Same thing, a lot of our PhDs have published like hundreds of publications in computer science, classical AI and security with tens of thousands actually of citations. So it's a pretty proper deep tech that we're going to be covering a bit. Good. Let's jump directly into the what we're doing. As I said, that's the first thing we want to cover. Again, more reliable applications without wasting time. That's ultimately the goal. If we get there, I'm sure everybody on the call and most of our industry is extremely happy. The idea is to prevent production incidents before they actually happen. It's great. We've been trying to do it for many years, and the data doesn't show that we're quite there, right? The secondary goal is obviously to cut time to resolution from days to minutes, right? When a problem occurs, rather than waiting in queues and spending time to figure out who's going to fix it, how to reproduce it, how to fix it, test and deploy, to be able to do that extremely fast when those incidents actually happen. And finally, it kind of enables kind of a safe and reliable use and adoption of AI-generated code. We're going to see some data how that's a challenge today. And again, it's a good thing that that's the number one questions people ask me when I speak about those topics. AI will not replace developers. That is purely my opinion, but I think it's shared by many. But it will actually amplify our impact. We'll be able to do much more things much faster and then focus on the important things, kind of building new features, new capabilities, architecting them, etc. Going to the problem specifically, right? What we're doing, right? Autonomous self-healing for backend applications is the first focus. Again, as I said, 90% of autonomy, right? The idea is to identify, reproduce, fix, validate all those software defects without having us as humans to waste time, right? And end up at a final code review step, right? We still maintain this, as I said, the 90%. We have to validate. We control the narrative and decide what goes to production. It is precision-driven, which means that we're using multiple agents to decompose the problem on the individual problems, then select what optimal models can help and solve with them using a best of n, orchestrate all of those to maximize precision, which means how accurate it is, and ultimately minimize or remove most of the hallucinations or partial solutions that we're getting. And we're seeing a lot from the AI-generated code. Reproduction is always the first step, right? Every single fix begins by confirming that it's a real problem. That's very important. Kind of typical test-driven development. Pretty much you have to enrich the issues through correlations with logs, commits, observability, different signals, and historical fixes before even attempting to fix it. Again, Lazar is going to speak about this observability and telemetry and how we actually use it as well. And then the last piece is the intelligent abstention, or kind of saying, no, I cannot help you with this unless all of the gates and quality checks have actually passed. So in a way, don't create pull requests if it's obvious for us that one of the tests is not passing, we're not able to reproduce it, etc. And the goal at the end of the day is, again, as developers, that we only see validated pull requests, right, directly into existing workflows. So you don't have to set up new IDEs or new environments, etc. It just comes in GitHub as a pull request. You see it, you get a good explanation. But anyway, I'll show a little bit later some of those pull requests, so then we can see better what we're talking about. What is the problem and why we're doing it? As I highlighted, there is a growing demand for application maintenance, right? As I call it, application reliability engineers, that I believe it's the right term for. And the reason is what we're seeing is AI, as we said, it's definitely accelerating the development speed. We're seeing much faster completion of tasks, more tasks being generated, pull requests being double linked into from an output perspective. So there's definitely adoption there, right? But we also see data that there is a quality trade-off, as we call it, right? Which means that the quality of those commercial applications and projects are actually dropping down, right? It takes longer to review the pull requests, so we're wasting time. Hence the demand for maintenance, right? The code churn more than doubled over the past year, which means there is a quick prod patches of fixing something or removing it within the first 2 weeks of deploying to production. Duplication code has 9x over the last couple of years, and there is delivery stability of production application, bugs, etc. The size of the pull request actually more than doubled as well. So that's clearly, there's lots of the signs how we historically been measuring quality, and we're seeing those going down. So in a way, we're getting this trade-off, boosting developer velocity, but quality and maintainability is actually dropping. So what we're getting, cursor example, just a couple of weeks ago, I think Cornell sent this out. We're seeing in the first 1 to 2 months, like great improvements, more commits being created, the lines being added have increased like 280%. But then after that, like within after 2 months, the effects actually disappear and sometimes it gets negative. So all of these data, I have the quotes underneath, but it's kind of mixed messages what value we're actually getting. And I think this is where the autonomous application maintenance it's really needed. Again, software is breaking faster than we fix it. That's pretty much what it is. The 400 billion number here that we're seeing is how much money are wasted every year just by the Fortune 2000 companies in production incidents. And the most staggering effect here is the 92% on the side, that 92% of those incidents already have shown something as a warning sign, either in telemetry or as a bug. And that's exactly the reason why Lazar after that will tell you, hey, if we're able to catch those and preventively fix them, we might be able to be saving almost all of it, 92% of this 400 billion. So that's kind of, it is exciting future. So I hope that we get there extremely fast. How are we doing it? As I said, let's jump directly into a quick demo that I'll try to actually show you directly into the LogicStar system. Here we're looking at one bug that LogicStar found on its own. As I said, we have 2 major features here: the ability to find issues autonomously, and then the ability to actually fix issues that you're already aware of. In this particular case, we have a very interesting issue where we're actually duplicating 2 requests in the queues. And what can happen that can actually cause assertion failures after that, being able to kind of kill the runner and then waste a lot of efforts to actually run it again. So kind of compute tokens, you name it. The great thing is that the agent fully autonomously identified that. And the first thing that what it does is actually creates a test and kind of the ability to actually reproduce it. So let's actually jump quickly into the test. I won't bother you too much, right? But let me here just make it a bit larger so we can see a bit more. Okay. So when we go into the test, here it is. It's loading. We can see that we actually first create the mocks that to make sure, hey, we're actually creating these examples, then create the actual tasks again after that, right? And then we actually run them again. So we have to schedule them, confirm that they fail, right? Then we actually create a couple of different workers. I'm running the wrong test, sorry. Okay, this is the internal validation test. Sorry, I'm backing up a little bit. We have 3 different types of tests. The final one that you're getting in the pull request is the unit test, as I highlighted. And this is the one that you actually care about. As we said, creating the mocks, scheduling them, making sure they actually fails, create the workers to confirm that when you're having 2 workers, one of them will fail, doing multiple retries. I think then we're actually doing them here, and then confirming that they fail. And ultimately underneath, we have a sandbox execution environment where we actually run those tests and confirm that they should have been failing. In this case, 1 out of the 30-ish so tests were failing before. And after we find and apply the proper fix, we actually see that this actually test will disappear. So this is the full run, kind of the summary, and we can see here that there was this 1 test failing. So that's kind of the first step that we described before. You have to kind of validate, reproduce, figure out how you're going to test it, and ultimately you come up with a solution that we were able to validate. In this case, we can see here in line 186 that we actually tracking the tasks that it's supposed to be requeued, right, to make sure that it's there. And then let's see the next change. We get line 2017 here. We actually check that we do not have this task scheduled and update the associated utility functions actually underneath to make sure that the whole file works. Automatically, we get the pull request, which is great. And just quickly jump into GitHub to see how the pull request looks like. Again, similar description, describe what it is. You see that all the tests have passed in this case. You see that we have a great test coverage. And then our team have quickly look at it and ultimately merge the pull request. So this is kind of the final 10% of the work needed to do all of the work, outside of the fact that we're able to kind of identify the issues fully autonomously. So with that said, moving in terms of how we're doing it and why we're doing it, the initial setup is simple, right? You have to kind of set up your GitHub or just Git repositories, any sources of bugs that you have. As I said, LogicStar has its own bug finder, but you might have many others, right? As well as telemetry signals that Lazar is going to speak about it later, like observability, your own Datadog, you name it, and any customer bug reports that could be coming. That could be in Jira, Linear, you name it, and it's there. What LogicStar does, it kind of correlates all of those points and fully autonomously on the back end, pretty much while you're sleeping, as soon as something comes in from any of those signals, kind of triages and reproduce those issues, figure out if it's going to fix or validate it. And every time, if any of the cases, if any of the gates fail, it will abstain and say, okay, I cannot help you with this. When all the gates are passing and you have extremely high precision and certainty that everything is good, then you can create pull requests and only then give it to the developers for this final code review that we speak about. I'm not going to waste your time with another example, but we can actually jump hopefully during the Q&A. How this is done, I'm just going to highlight what is the difference between all the other tools out there. There's lots of hype. Everybody's claiming, okay, we can do this, we can do this. Reality is a bit different, right? The important thing is we have a very deep and structured context, right? To create a repeatable and explainable context that you can restart at any single step of the process. So that's important. So you know why the problem is there, where it is, what is leading to the problem. That's the number thing. Multi-signal engine, pretty much this is the ability to surface the highest value reproducible true positives first, right? Allow us to identify this is the real problems that we can deal with, they are real, and we can fix them. For everybody else, we're continually using our manual steps to how we can fix things today. Everything is aligned with the style of the team, so we have this continuously engine at the end that fixes and tests local conventions, pre-commit checks, specific linters, etc. Pretty much the style that your team is used to. So the pull request looks and feels like what one of your colleagues would have done. Validated autonomy. This is the idea that we run the secure sandbox as I highlighted, but we are removing the hallucinations and any unsafe changes, right? To prevent us as humans having to review this and manually identify those issues, right? So ultimately not wasting our time. There's a human oversight. We only automate 95% of the works, but ultimately the teams stay in full control at the end. Pretty much what enters in production is reviewed by a human every single time. Maybe that will change in the future, but that's it's going to be a separate discussion. Finally, you're getting results, right? Well, other tools will generate guesses, sell you tokens, do auto completion, and ask you what you want to do. Here, we're actually creating a predictable outcomes, a validated bug fixes and proposals in the form of pull requests, right? There's nothing in between. You don't know what you're getting. And over time, this is actually growing advantages because we continuously learning with our reinforced learning what you like, what you dislike, how you actually like to do things, what's important for your application, and which parts of the applications are maybe obsolete or just tests that you don't care about. And that allows you to have much more targeted and precise choices of what to fix and when. Given the timeline, I'm just going to quickly go a bit deeper into the how. As you said, the most important things is to be able to have benchmarks to test if this end-to-end system of multiple agents is correct. Really kind of validate and test, are we getting better or worse? The first thing, as I highlighted, this is the SWT benchmark. It's our ability to test things. And we're saying, if you're not doing tests, then your precision is very low. If you're able to add regression tests and then unit tests and then AI tests, and when you do all of those, you're already increasing, actually reducing the workload of seeing wrong issues by 6x, right? And this is the SWT benchmark. We're kind of a leader in that board right now, and we've been for a while. And that's one of the important pieces. The other big way of measuring things is the SWE benchmark. As I highlighted, this is the most common industry standard. You will see almost everybody, like you see every single dot here is an example of either large language models alone or an agent from that model that is there. And you can see us right as here, we're kind of leading the state-of-the-art performance there. Again, the bad part of this benchmark is focused on open source libraries, so they're not very representative for real application issues. And this is where we actually created what we call the SWA benchmark, which is kind of allows you to really see that real applications and real problems in those applications is what matters. We published that recently as well. And you can see that compared to the fake or just a library type of issues where even the models likely trained on those fixes because they're open source, we actually see considerably drastic decline in the capability of the agents and models to deal with those. And this is where we come in, trying all of these decline and false positives here, in a way, false solutions. We want to actually filter out and just identify which issues do not require more information, and they can safely produce pull requests without requiring more data from the developers. So they can just assign it to a code reviewer and push it forward. With that said, I'll pause. We have a special offer for all LocalStack users to actually start using LogicStar, because we implemented it. We've seen how great it can work on the LocalStack code base as well, and some demo applications running LocalStack. And we're going to push a blog post how we plan to integrate LocalStack as part of the execution environment, so you can very quickly get much better results. And I'll pause here so we can start with some questions to make sure that we have enough time for Lazar as well.
Hey, all right.
Hey.
Yeah, I'm back.
Perfect.
Hey everybody. So actually, let's see if we have questions in the comments, and if not, that's great because I have questions. Cool. It doesn't seem like we have any in the comments yet. But, all right, so let's start from the beginning. How does the agent decide whether it should fix a bug versus escalate it to a human?
That's a very good question. Pretty much what we do for all the issues that we look at, right? And then we can have some filtering there as well. We have some filtering, for example, if that looks like you need a database migration, we say, I don't even try that, right? It's crazy. If it's some cloud deployment, you have to be changing how your cloud is deployed currently, we don't do that. As you said, we're currently focusing on the backend part of it. So that there's a lot of filtering and some agents that actually identify this based on the description of the problem. And then once an issue is identified, yep, this qualifies for fixing. It is a bug. It's not some new crazy features that require product owner to define what it's supposed to do and what the business logic is. Then we say, now it's a fair game for us to start working on it. And then we follow the steps. As you said, we have proper gates. We have to investigate. We have to reproduce. Then we have to be able to figure out if there is a fix that can actually addresses the failing test from the reproduction. Then we have to identify all the unit tests that are related to this specific fix that you already have. A lot of times, as we said in the example that I show, we actually add a unit test if it doesn't have it, so we have a code coverage. And only that, or every single gate has to pass. Only that we said this is something that we have extremely high certainty and we can create a pull request for. If we don't, we say, hey, that's not something that full autonomy can deal with. Please assign it to a human. The human will have to review it and work on it on its own. Sometimes there's additional value that we can provide, like we were able to reproduce it alone, but the fix was not able to be identified. So that might actually save 50 to 80% of the engineer time as well. But the full autonomy, it's you have to pass every single gate to make sure that you have the high precision.
Gotcha. Okay, that makes sense. We do have a question from our audience. How does your agent differ from Cursor, Claude, Code, and etc.?
I mean, in many different things. The number one that I would say is, again, it's working fully autonomously. You don't have to prompt it to do anything else, right? That's number one. Second of all, it breaks down the problems in a classical computer science, but we don't expect that the large language models will figure it all out, figure out the right context, figure out what tools to call, which tests to run, how many tests to run, right? And that enforcement allows you to kind of remove most of those false positives, right? So that's kind of the number one thing that you can say. And you log in the morning and you actually see, hey, for 40% of my bugs that came overnight, or my bug backlog that is coming for next release, I actually have already pull requests, so they can actually go and change it. Once you have that, in a way, think it this way. This LogicStar is as if you actually had one of your teammates working this problem overnight, right? And then they actually assign you the pull request. Once you get the pull request, you're just doing the code review. If you have to tweak it a little bit, sure, you can use your Cursor, etc., or whatever your preferred IDE is. You can still run the code review tools that are out there in case you believe that there might be some issues being introduced by your coworker, in this case, LogicStar. So that's kind of the biggest thing. So we're trying to validate and abstain when a solution is not there, right? So we end up abstaining maybe half of the time. That means every time that we abstain, it is us saving your time for you saying, yeah, that's a solution that might work okay, it doesn't pass one of the tests, please give more feedback. So we're not wasting the developer's time to having to chat back and forward, evaluate if something is correct, provide more context, provide which tests they are if they're not there, etc. So we're trying to fully automate these parts. And again, only in the cases where that's attainable without asking a developer questions. Otherwise, you're getting into this standard, what I call co-development workflow.
Okay, so that makes sense. Oh, okay, we have a comment. Oh, actually, no, a question from our very own Waldemar regarding Hey, Waldemar. So regarding your SWA benchmark, is it focused on any particular application architecture? For example, monolithic, serverless, microservices? Oh, it's a great question.
It is pretty diverse. The specific SWA benchmark, it's a diverse set of hundreds of open source projects, like real projects that have everything else. So we haven't discriminated. I mean, the one that we've built and published first was specifically focused for Python. So that's one limitation. But other than that, there's no limit. Internally, what we do, we actually call what we call our design partners benchmark. Also, kind of the people that we work with, local stack included, that we kind of run in our production environment. We maintain some of those issues and we kind of keep on rerunning them to make sure with every single release and change that we make to the whole platform that we are not kind of degrading the performance, right? That's really important because, I mean, over the past year and a half, we've tested, I'm not going to say hundreds, but yeah, it's hundreds of agents, tools, MCPs, combinations, just to find that the majority of them went out, it actually degrade the performance of the end-to-end system. I mean, we've seen that even with the proper LLMs, right? They just either not call the tools or the MCPs, or just because how they're fine-tuned and trained, if you just give them something else, they just get derailed and go into some weird tangential that ultimately lowers the final performance, right? In some weird cases, they might help, but on average, they end up getting worse. So that's why that's ultimately the SWA. So it's pretty diverse is the short answer.
Gotcha. This is very exciting, actually. Just the idea of being able to come in the morning and just have pull requests instead of bugs. I mean, I think this is going to change the game. Like, honestly, I really think it is. And thank you so much for your presentation. I mean, like I said, I was having technical difficulties, but I heard it all and it was just like kind of mind-blowing. So very excited to be able to use this in the future. And I'm sure engineering teams are, definitely feeling excited as well about this. So awesome work. Thank you so much, Boris. Yeah, like thanks for joining us and all of that jazz. So next up, we have our very own Lazar Kanelov, our engineering manager, and he's going to talk to us about creating self-healing software systems via effective usage of telemetry data and AI agents. Thanks so much for joining, Lazar. I will let you have the floor.
All right, thanks for having me again. I'd like to give a short presentation for the audience in order to contextualize a bit before jumping into the technical details. And here's the agenda for today. I'd like to cover several key points. For example, the role of telemetry, what high-quality telemetry looks like, why telemetry alone isn't enough, and the role of large language models in this process. Also, what a self-healing system looks like, both from a technical and process perspective, and of course, what are the benefits of this model? Why would you do that? So let's get started. The first point is super important in my view because this is the actual prerequisite. We cannot really automate in a meaningful way without observability. And basically, telemetry is one of the key pillars to really understand what's going on in your system, especially in production. So the telemetry is the basic entry point of our system. But it's not only about the telemetry, but the actual quality of this telemetry data, because you can see on the left-hand side an extremely bad example of telemetry data and much better example on your right-hand side. Ideally, your telemetry should be rich in terms of context like services, inputs, environments, etc., even some correlation IDs. So basically, if you have this good telemetry, you are almost done for automation. But in reality, telemetry alone isn't enough. Telemetry basically tells you what really happened, but not what to do about it. So you need additional component to help you with this analysis and the actual summarization and classification of the information. And that's why we need large language models. They're extremely good in this, and they can basically turn your telemetry data into some sort of a structured intelligence so that we can have another system like LogicStar in our particular example to basically work with this structured intelligence and provide meaningful outputs. All right, here I have a tech architecture of such a system. I'd like to very explicitly underscore that this is a tailor fit for WackelStack. I have created this application as a proof of concept, but I think most of the concepts, they're actually reusable. And even if you're using a different technology stack or you have a different architecture, you can still use some of those ideas and implement something very similar. So let me walk you through this architecture. On the left-hand side, we have our data source. In our particular case, this is Tinybird because at WackelStack, we use Tinybird as a data warehouse. And for those of you who are not familiar with Tinybird, it has this nice feature called pipes, which are in essence RESTful APIs. So basically you can consume your data via RESTful APIs. And you can imagine that this is perfect for integration purposes. So the next component, the next pillar is the actual data processing. And here we have several subcomponents. We have the data fetcher, which is basically responsible for fetching data from Tinybird. After that, we have the filter, and this is super important because we want to filter some of the telemetry data. And I can give you here a very concrete example in the context of WackelStack. For example, we see a lot of issues related to licensing, and it doesn't make sense to materialize those issues into GitHub issues and ask the AI agent to fix them. It doesn't make sense at all. That's why we need to filter them, and we have this component. And also the last part of this pillar is the actual processor, because as I mentioned, we are about to feed this data into a large language model. And as you know, large language models, they have some limitations like the tokens limit, for example, and we need to make sure that we are not overloading the large language model with too much data. So yeah, this is the data processing pillar. The next one is the heart of the system, the actual large language model. In our case, we're using the large language model to basically generate some GitHub issues. And here it's all about prompt engineering. I'm about to show you a very detailed example with the exact prompts that I'm using to generate them. And the last part is actually to use this data and call the GitHub API and create some real issues following the template so that we can have LogicStar or any other smart agentic system working on them and providing automated fixes. So this is from a pure technical perspective. From a process perspective, it's very simple. We have this weekly automation cycle. So this system is running every Monday. So basically every Monday we have a new batch of issues. And then we have LogicStar working on those issues and producing some fixes. And of course, at the end, as Boris already mentioned, we have the human in the loop. We have engineers reviewing those fixes, and we were happy with them. We just merged them. So I think at this point we have enough context. So I'm about to switch to PyCharm to show you some prompt engineering. As I mentioned, the AI component is all about prompt engineering, and we need to have very good prompts in order to produce meaningful results. And this is the prompt that I'm using to generate the issues. As you can see, it starts with you are a technical issue reporter based on the following error telemetry data, generate a clear and concise GitHub issues. And here, as I mentioned at the beginning of the presentation, it's very important to have a lot of context in order to generate actionable insights. And in our particular example, we have service, operation, status code, the number of affected organizations, versions, subscription plans, and of course, the error message itself. And I'd like to explicitly underscore those because we need to also evaluate the impact of the issues, and this is super important. Also, we have some generic guidance for the model how to create those issues. And this section, again, is super important. Do not include, because as I mentioned, we need to feed this data to LogicStar, and ultimately we want to have it in a very pure form without any additional analysis from this large language model, because LogicStar, as Boris mentioned, is specialized in providing fixes, and they have very sophisticated system for this. So we don't need this model to provide any additional analysis. That's why we have this step here. Do not include, for example, steps to reproduce or let's say some sort of a brief technical analysis. This is not needed. That's why it's super important to be explicitly stated here. And also, as I've mentioned, we're running this system as a GitHub action every Monday. So basically every Monday we end up with a new batch of issues. And now I'm about to show you a very interesting example. This issue is automatically created by the system. You can see here that we have this label called telemetry data in order to differentiate with the rest of the issues that we have. And you can notice that the actual issue is following the template defined in the prompt engineering. We have a very short summary. In this particular case, a 500 internal server error occurs during the S3 put object operation, resulting in an exception due to attempting to read a closed file. We also have this impact information. This is the metadata that I already mentioned. For example, in this particular issue, the number of affected organizations is 7. Also, we have several versions affected here and also several subscription plans, which means that this issue is very important to be fixed. And of course, the full traceback, which is the most important part of the whole context. And now the beauty of it, we already have a fix by LogicStar of this. You can see the actual investigation report with all the technical context, the bug description, which is more or less copy of the already existing issue in GitHub. And the most interesting part, in my view, the root cause analysis and the bug fix overview. And you can see here that LogicStar spotted that in this particular case, the request.mime type is causing issue because of the way this thing is working under the hood. And actually the bug fix is very interesting, just to replace this code with a manual parsing using the headers, which is super simple but very effective fix. And you can see on the right-hand side the actual code change. It's super cool. And also, as Boris already mentioned, not only the code change, but also some tests in order to verify that this thing is really working, and also some reproduction scripts so that we can rerun this and make sure that this is working. And if we are confident enough with this fix, we can just open a pull request and merge it, which I think it's awesome. Which means that we can also discuss some benefits of this approach. I think the obvious one is better developer experience, because we can focus more on building versus doing some analysis of telemetry data, bug fixing, etc., etc. It's much more scalable. You have this predictive capability and, of course, high reliability, because if you have tons of high quality telemetry data, you can imagine that you can improve your system proactively without waiting for bug reports and some other issues coming from your production environment. So I think this model is very good for any kind of organization with a high quality telemetry data. And yeah, this is pretty much all about it from my end. If you have any questions or discussion points, happy to answer. And I hope this was useful for you.
Very, very, very interesting. Thank you so much, Lazar. Let's see.
You're welcome.
If we don't have any questions from the audience, I've got questions. That's okay. So let's talk about, let's start here. What's the minimum level of telemetry quality or coverage needed before an AI agent can make a reliable decision?
I think there are two things here. The first one is to have a lot of context about the environment and the full traceback in order to basically understand, even if you are an engineer, to understand what's going on with the system. And then to have this additional large language model to create insight from this data and materialize it in, let's say, linear issue or GitHub issue, and have an intelligent system like LogicStar to work on it.
Very cool. Do you have can you share a little bit of insight on how LocalStack and LogicStar are going to be working together, and how that integration is going to work? Can you give us a little bit of details behind that?
Yeah, definitely. We've had a very productive chat with Boris on that topic. And I think we have a lot of useful vectors, I would say, to achieve this collaboration. One of them is to, let's say, even leverage our chaos engineering capabilities, because as we all know, we support this super cool feature called chaos engineering. And for example, LogicStar could actually use this feature to simulate some edge cases and make sure that we are finding some very weird issues, which I think is especially applicable nowadays with all those outages in the public cloud providers.
Very, very, very good use case, I think.
And a lot more.
Yeah, I'm sure. I could definitely see a lot of these happening, especially with the chaos engineering. I mean, not like AWS ever goes down or anything. Okay. One more question I have for you.
All right.
How do you prevent AI agents from acting on noisy or incomplete telemetry data?
Yeah, absolutely. That's a great question. And that's why I mentioned that it's very important in your system to have some sort of a filtering and to decide how to filter the noise from the signal. And in our particular system, for example, we are using some sort of metadata, for example, the number of affected organizations. And also we skip issues related to licensing, because ultimately we cannot really do something meaningful with those issues. So I think if you have really high quality telemetry with a lot of metadata, you can build a very sophisticated system to basically extract what's really meaningful and skip any noise coming from the telemetry data. Because you can imagine that at scale, you could have a lot of noise. And if you don't have proper filtering, this could end up in a very inefficient system. And even expensive to run, I would say.
Absolutely. Okay, that makes 100% sense. If anybody else has any questions, feel free to either drop them in the chat, right now, because we're about to wrap up. But Lazar is also, a part of LocalStack, so you could probably find him on our community chat, community.
Oh yeah, absolutely.
Slack. So if you are not a part of the community Slack, definitely join us there. You could ping Lazar and other folks for more questions and pick their brains there. Thank you both so much for coming on today. Thank you everyone for bearing with me while I navigate my technical difficulties. These were amazing sessions, and very happy to have you all with us live. And as always, thank you all for being a part of the Local Stack community, and we will see you on the next meetup.
Thank you, Kaya, Lazar.